Hello, this is Romel Petya, Abhishek Paul, and Donald Leshy from Team 135 presenting our project on music generation with machine learning. So why are we interested in music generation? I find as a casual musician, I'll often be playing notes for a few seconds, which creates a nice melody. However, I'm not really skilled enough to figure out what should come next. So I came up with this project because I wanted an application that can take something that I've recorded and create an extension, with the extension being some new music that sounds good when played after the melody that I recorded. For a bit of background on what's already been done in this field, most music generation we've seen is random, where a model looks at many examples and learns to randomly generate new pieces of music. Our task is a bit harder because the model has to consider input examples as well as extension examples. After we started this one product known as Amazon Deep Composer was announced that tackles this problem, but other than that, nothing is really commercially available. So this is a new area of research that we thought would be fun, interesting, and useful for aspiring musicians. With all of this in mind, we had a clear goal of creating a music composition application using neural networks. In order to create a solution, some key requirements were established. First, we needed to decide how to represent music as data. So we chose MIDI, a file format that contains instructions containing information about pitch and when these pitches are turned on or off. This is further interpreted as piano roll, which is a 2D array containing time on one axis and pitch on the other. So we chose the piano roll representation over others due to its simplicity when compared to things like waveform data or MIDI instructions themselves. For the dataset itself, it also needs to be simple enough that the model can reasonably learn. So we wanted our data to be monophonic, meaning only one note is playing at any given time. We wanted to use a reduced range of notes, and we want the duration to be short. We'll talk a bit more about how we accomplish this when we talk about the system flow. For the model architecture, we chose recurrent neural networks because of their ability to process sequential data such as audio. And for the user interface, we expect it to interface between the user's keyboard, their computer, and the model, and eventually return to them a 5-second melody extension after they played their own 5-second melody.
Our project was essentially broken into three parts. The data processing part, where we acquired and transformed the data, the model training part, which involved creating and tuning the model, and finally, the creation of the user-facing interface. Unlike images and videos, the number of machine learning projects that focus on music are limited. So we had to build the entire data processing pipeline from scratch, and this part took the majority of our project. The first part of the pipeline consisted of reducing the complexity of the dataset in order to make it feasible to train. In order to reduce the complexity, we first converted the music from polyphonic to monophonic by taking a random sampling at each time step and by also making sure that the patterns were preserved. In order to further reduce the feature space, we decided to constrain our design to 2 octaves. We decided on the range of 48 to 73 since it had the highest frequency of notes in our dataset. In order to achieve this, we shifted the notes back into the range 1 octave at a time. The next part of the pipeline was to make sure that the inputs were consistent, so we could use it in the model. We first normalized the tempo so that the time steps for all the songs translated to a consistent unit of time, which ended up being 0.02 seconds per time step. With a standard tempo, we then split the music into consistent 5-second segments, and this resulted in a standardized 240 time steps per segment. In order to feed the data into our model, we needed to do some further data transformation, such as one-hot encoding the data so the RNN could understand it, and also creating the melody and extension pairs which the model could learn from. We had to go through many iterations in order to create the data processing pipeline, as we faced many different problems which required to be fixed. But in the end, we ended up with a robust pipeline which we could easily tune and that could take any MIDI input and feed it into a model.
So after the dataset's been transformed, it's used to train the model. There are 3 key steps in the training process. First, a model is created. We are using a variant of recurrent neural networks called the gated recurrent units as our model. Secondly, this model, along with the dataset, is passed into the training code. The training code generates a melody extension for each input melody as shown in this figure. We tested many variations of how to generate extensions for training, and we went with this one because it accurately represents testing conditions of the model. So first, the melody input is passed through the model one note at a time, as you can see in the left half of the figure. For each note, the model outputs a hidden state and a new note. We don't care about these notes being generated, but what is important is that the hidden state is continually updating itself based on all the notes it's previously seen for this melody. Once the entire input is read, the final output note is what's useful. So we can see on the right half of the figure that this is the first note of the melody extension being generated. This note is then passed through the model with the hidden state, which generates a new note and a further updated hidden state. And this process repeats until an entire melody extension of notes has been generated. Finally, what do we do with these generated extensions? Each melody has a true extension associated with it, so we compare the generated extensions with the true extensions. These differences in these comparisons are used to calculate cross-entropy loss, which updates the weights of the models, and accuracy, which helps us gauge the model's performance. Custom accuracy metrics, zero and non-zero accuracy, were also developed to measure how well the model was generating specific notes versus how well it was generating silent time steps. This helped us reduce bias in the model's ability to generate music. So these steps of generating extensions, calculating metrics, and updating the model are repeated until satisfactory metrics are achieved.
Once the model training phase was complete, the next step was to establish an end-to-end user-facing product. In order to accomplish this, we had to build a framework that interfaces our MIDI keyboard with our Python code and thus our model. This framework will read and interpret MIDI events, and it will construct a MIDI file. We utilize a Pygame library to poll the keyboard for 5 seconds once it is connected. During polling, if a key is pressed, a MIDI note on message is sent, and once the key is released, a MIDI note off message is sent. We save these MIDI messages in a data structure, and we later parse them to extract necessary information such as what note is being played, the timestamp, and the volume of the note. Next, in order to construct an input MIDI file using these MIDI messages, we utilize the middle library to initialize a track object and setting certain parameters such as track number, tempo, and time signature, and calculating a delta time between each of the MIDI messages in order to place the appropriate note at the appropriate time. This input MIDI file, now representing the recorded melody, is saved to a directory. Next, this input MIDI file goes through the exact same data transformation steps as during the training phase, including ignoring notes out of range and changing from polyphonic to monophonic. After these steps, the MIDI file is now played back to the user such that they can hear what is being fed into the model. This encoded melody is then passed through the trained model, and the model will generate an output. The model output has to be converted back into MIDI, so this involves undoing the data transformation steps and doing post-processing cleanup, such as to prevent rapid changing of notes in consecutive time steps in order to prevent unappealing music. Finally, the output piano roll format is converted into a MIDI file and played back into the user interface. And now just to summarize, all of this happens in real time. So the user will play notes on the keyboard for 5 seconds. It will generate an input MIDI file. This MIDI file will then be going through the exact same data transformation steps, fed through the model will generate an output, which is then played back to the user. An important thing to note here is that this entire framework and infrastructure we had to build ourselves since there's no native way of doing it in Python libraries.
I'll be talking about how we verified that the project met its goal. The goal of the project was to create a machine learning model that could learn to generate extensions from a given input. So we measured the accuracy by comparing the generated extension to the true extensions. The model was able to learn from the data as we found that the overall training accuracy was 76%. To show that the model could generalize to new music inputs, we presented it with validation data, and the overall validation accuracy was 48%. These values show that the model is able to effectively learn from the training data and, to a certain extent, generalize to new data.
So now that we've seen how the model works and some of the results, let's actually see it in action. So first I'm going to show what the user actually sees when they run the app. So they start it by running the Python script, which gives them a quick countdown of when to start playing. As they play notes on their keyboard, the relevant MIDI data is shown on the interface. And first, the audio of what was recorded is played back, and then the audio of what the model generated is played back. So now I'm going to play the familiar melody of Twinkle Twinkle Little Star, and while we don't expect the model to complete the melody, we do hope for it to play something that sounds musical. So this whole project came about because I wanted an application that would generate music based on something that I came up with. So let's see an example of that. Although our model performance has a lot of room for improvement, we wanted to emphasize the fact that we developed a very useful framework for the development of music generating neural networks. This framework allows us to transform any MIDI dataset into one usable for model training, and furthermore, the training code and user interface developed can be used with many variations of recurrent neural networks. This framework can continually be used to further the research of music generation with machine learning. Now I'm going to talk about the plans for the future of this project. One thing we wanted to expand was our data complexity reduction transformations. Keeping in mind that piano roll is a 2D array with a note axis and a time axis, all of our complexity reduction was focused on reducing the complexity of the note axis. Our list of data transformations was constantly evolving as the project evolved, and very late into the project we had the idea to reduce the complexity of the time axis. Each time step represents 0.002 seconds of time, but if we could somehow increase that value, the model would have much less information it would need to learn from. Another aspect that could be picked up by future researchers is the model performance. Simply by varying the input models and datasets into our framework, extensive research can be done without any need to further develop any code. A team with much larger computing resources could create a much more powerful model, much like Amazon did with their application Deep Composer just last December. Furthermore, this concept of mixing and matching datasets can be applied to create specialized models. By training a model on a specific dataset of music, such as varying keys or genres, a model can specialize in those types of music. Finally, if a model is eventually found that has strong performance, we can easily chain outputs of the model together. With just a short input from the user, an output generated can be fed back into the model to generate a new output and repeated until an entire song is written. All of this is possible through use of our framework and better resources.
There were a certain number of challenges we faced with this project, mainly because generating music with machine learning is a relatively new field. The three main challenges we faced here was the long training time, finding a way to represent our data, and certain issues with finding the appropriate accuracy, which we call the zero problem. In order to obtain better models, they require a longer training period. And since we're time constrained during this project, there's only a certain number of models we could train. So this limited us in exploring different models and different parameters in order to improve the model. In order to reduce the model training time, we focused on applying data transformations and reducing scope. There's 2 to the 128 combinations of notes per time step, which is an impossibly large amount of data. Thus, to further reduce the training time to just days of training, we had to apply data transformations to reduce the complexity to 26 combinations. And now just to summarize, we reduced our scope to focus on training and testing one architecture, the RNN model, in order to get a better result rather than training many poorer models. Another challenge we faced was finding a way to represent our music, so we explored 3 different options: wave data, which is raw musical waveforms. We also explored MIDI instructions, which provide note on and note off events, as a way to represent the musical instructions. Furthermore, we explored MIDI as piano roll, which is a 2-dimensional array, on one axis featuring the time steps, and on the other axis featuring what pitch is being played. Time was spent researching each of these options in order to find the one that machine learning can best learn from. Ultimately, wave data was too big, MIDI instructions contained inconsistent duration, and we ultimately selected MIDI as piano roll because it's very simple for the model to learn. To summarize, we solved the longer training time by reducing the complexity and scope of our project, and we figured out our data representation by researching and selecting the option that is the easiest for the model to learn.
Another one of the significant challenges that we had to deal with was that initially the generated extensions were completely silent. For music in general, at any given time step, it is more likely that music is silent than any of the other 25 notes being played. Since machine learning models look at the probability of specific notes appearing, it produced silent outputs in order to maximize its accuracy. In order to identify the extent of this problem, we introduced custom zero and non-zero accuracy metrics and made significant data transformation steps. Instead of deleting notes which were outside the required note range like we did before, we instead shifted them back into the range one octave at a time, so the sound was preserved. We also created a function which eliminated all music segments that were silent for more than half its duration, in order to reduce any bias towards silent outputs.
So this is Rommel talking about my contributions to the project. So for the data processing part of the system flow, I was responsible for the data representation research, as well as actually acquiring a data set and researching possible data sets that we'd use. I was also responsible for either creating or assisting in creating all of the data transformation functions that we talked about. For the model training section, I was responsible for creating different forward pass functions that we iterated through until we found one that we thought was the best one. And I also created the custom metrics of zero and non-zero accuracy, which helped us identify problems with the model. And finally, for the user interface, I helped Donald actually record the MIDI events and save them into a MIDI file. And I also created a function that smooths out the outputs of the model to create a more natural sounding piece of music.
I'm Donald, and my key contributions to this project were mainly on data processing and on the user interface. I worked with the team on researching ways to represent music and assisting in writing all the data transformation functions, such as processing the MIDI songs split by intervals to generate pairs of the melody and the subsequent extension to the melody. Furthermore, for data processing, I also implemented the silence threshold functionality to exclude MIDI songs containing more than 50% silence. I was mainly responsible for the user interface, so to establish the necessary framework and infrastructure in order to establish our end-to-end pipeline. So I had to research all the necessary libraries and how I can repurpose certain libraries in order to accomplish these goals. I utilized the Pygame library and the middle library and the necessary infrastructure to create an input MIDI file that would later go through data transformation steps and being passed through the model. I worked on converting that model output back into MIDI format, which would later be played back onto the user in the interface.
Hello, I'm Abhishek. My key contributions to this project were in the data processing and model training parts. Data processing took the majority of our project as the entire data transformation infrastructure needed to be built from scratch. I was responsible for writing or assisting in most of the transformation functions. Specifically, I was responsible for writing the function which looked at the note frequencies, the functions which shifted the notes back into the required range, the function which created melody extension pairs, and the function that created the MIDI files from the model outputs. I also assisted extensively in the polyphonic to monophonic conversion. For the model training part, I worked with Rommel in creating the initial RNN and was mainly responsible for the different parameter tuning in order to get the best results for the model. One of the recurring problems was the long training time, and in order to improve the training times, I set up and ported our model to Google Cloud so we could get access to their better GPUs.
Thank you for watching our presentation. We hope you enjoyed our project as much as we did, and if anyone watching is interested in continuing our project and using our framework to further develop neural networks for generating music, feel free to contact us by email.